It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to lesson 3 here where we're going to continue solving rational equations. So now that we know how to solve them, we're going to practice solving them and kind of look at some examples and just get pretty good at solving rational equations. So solve for all values of m here. So again, the first thing I'm going to do is I'm going to check out my denominators to see when I'm undefined. Right away, I'm going to say m cannot equal positive 1 because that makes that fraction 1 over 0. M cannot equal 0 because that makes that fraction 1 over 0. And I'm going to move that negative up top. And I think I've got a GCF here. Here we go, m minus 1, which are perfect. So these are the values that would make me undefined. Now we've got to get our common denominator, which clearly is m and m minus 1. So this first fraction, here needs a factor of m. And this fraction here needs a factor of m minus 1. So now that I have a common denominator, all I need to look at is the numerator. 1m plus 1 times m minus 1 equals negative 1. So I get m plus m minus 1 equals negative 1. 2m minus 1 is negative 1. 2m equals 0, so m equals 0. But that's an extraneous solution. Why is it extraneous? Because all the way back up here, I said that m cannot equal 0. So this is an extraneous solution and we throw it out, which means we have no solutions. Which means we have no solutions to this rational equation. I cannot find any number that makes it true on both sides. That makes both sides equal where it's true. So solve the following rational equation for x. So I have 3 over x plus 1 minus 2 over 1 minus x equals 1. So I'm not a fan of this 1 minus x. I want to make that x minus 1. And remember, these are opposites of each other. There's an extra factor of negative 1. When those guys divide out, they leave behind the factor of negative 1. So to make that flipperoo there, I've got to add a negative somewhere. So watch what I'm going to do. I'm going to put that negative, boom, right out front. So what I did there again is I took this 1 minus x and changed it. But to do that, I had to throw in a negative 1. The way that I threw in that negative 1 is I just made that minus sign into a plus. So notice that's where the negative 1 went. Because that's much nicer now, because I know I need an x minus 1. I'm going to add that to the top and bottom. I need an x plus 1. And then over here I've got nothing, so I need both of them. I need both of them over there. I've got common denominator. Oh, first of all, I should have said x cannot equal negative 1 and x cannot equal positive 1. I always forget to do that. Look at your denominator and see who you can throw out. Because now I don't have a denominator. Now I have 3 times x minus 1 plus 2 times x plus 1 equals that. Well, that's the difference of perfect squares there. That's if you make a box for those, or realize it's the difference of perfect squares. Little distribution again. And I just got to clean this up a little bit. 5x minus 1 equals x squared minus 1. Going to move these terms over. Make it 0 equals x squared minus 5x 0. So this one always freaks us out because we just forget to take out a GCF and get x equals 0 or x equals 5. Which again, I'm just going to go back up here and check for a second. Can x equal 0? Can x equal 5? Yes, we're good to go. Alrighty. Here we go. Here we go. Solve these rational equations. All right. Looking at my denominators, that's where I'm going to start. X cannot equal -3. Oof, that guy I'm not a fan of because it's not in the right order. I'm going to do a flip here. I'm going to make that X minus 3, but stick a negative sign out front. Difference of squares needs to be factored. I'm also going to throw out +3. -3 and +3 are the values that will make me undefined. All right, let's get a common denominator here. This first fraction needs an x minus 3. This next fraction needs an x plus 3. I'm going to put on the top and bottom. And then this fraction's good to go because it's got both of the terms. So now we just look up at the top. 1x minus 3 plus 2 times x plus 3 equals 4. So I distribute equals 4. So 3x plus 3 equals 4. Minus 3, 3x equals 1, so x equals a third. Which is allowed because what numbers did we throw out? We threw out -3 and +3. 1/3 is good to go. So that is my solution. There's one answer to solve that equation, and it's 1/3 is the answer. Oof, this is beautiful over here. So first of all, I got to make that a fraction. So everybody needs an x plus 7, so x is not -7. And everybody needs an x, so x is not 0. So this first fraction needs both of them. X plus 7 needs both of them because it doesn't have anything in the bottom. Minus, well, this needs the x, so I'm going to stick an x out front. And then I'm going to move that negative up top. It's got the x, it needs the x plus 7. There we go, I got it. Don't start distributing yet because people always lose things. Just rewrite your numerators and then we can start distributing the madness here. But just rewrite it first. I know it takes an extra step, but just rewrite it because you're going to make less mistakes with pesky negative signs that just pop up. 5x squared plus 35x minus 3x squared minus 25x equals -3x minus 21. Two x squared, 10x. This looks much nicer now. I'm going to move all those terms over here. Plus 3x plus 21 equals 0. I can't GCF, so that means we get to AC method. This is fantastic. What multiplies to 42 that adds to 13? Well, I'm thinking 6 and 7. So I split the middle term there into 6x and 7x instead of saying 13x. And now I'm grouping. What times that? I need 7 there. So x plus 3 and 2x plus 7. So x equals -3 or x equals, well, -7 cut in half. -7 over 2. But I really shouldn't box those in. That was beautiful algebra there. I shouldn't box those in until I check up here. What makes me undefined? 0 and -7. I didn't get either of those, so those are both solutions. There's no extraneous solutions here. Both of them work. All right, last thing here. Let P of T model the population in thousands of people in a small county in upstate New York, T years after 2010, and the population in thousands of deer in this county, T years after 2010, is this function. Solve the equation P of T equals D of T. So P of T equals D of T. So let's solve this equation. So everybody needs a t and everyone needs a t plus 1. T plus 1. Need both. This just needs a t, top and bottom. This needs a t plus 1. So I'm going to rewrite it before I start distributing. First of all, t cannot be 0, t cannot be negative 1. Just taking care of my undefined values. 3t squared, I always get excited and just start solving. And now I'm breaking my own rule right here by distributing early. I apologize for that. Those go to 0. So 3t squared equals 4t plus 4. So let's get this equal to 0 here. And I'm going to ask myself, what multiplies to negative 12 that adds to negative 4? Negative 6 and 2. So split the middleman as I'm running out of room here. Negative 6t plus 2t minus 4 equals 0. I love factoring. So my factors are t minus 2 and 3t plus 2. So my solutions are t equals 2 or t equals negative 2/3, which we're talking about time here. You can't have negative time. This is negative time. So we're going to ignore that and go with t equals 2. So what does that tell me? Well, what is t? 2 years after 2010. So in 2012, what did we find? In the context of the problem, the population of people in the small county in upstate New York will equal the population of deer, right? The population of deer. In 2012, 2 years from 2010, the deer population and the people population will be equal. So hopefully you found some practice at rational equations here, and that's what we're going to keep on working on. See you guys